We've built our modern world around a relentless pursuit of absolute safety. When we engineer our power grids, our financial markets, or our aviation networks, we're operating with a singular, obsessive goal: eliminating every possible error. We engineer these systems to simply never go down, assuming that if we can just remove all local failures, we're going to achieve perfect stability. But we immediately run into a deeply unsettling contradiction. We all operate under this common belief that adding backup systems guarantees safety, right? If one part breaks, another just takes its place. Yet when we actually look at complex technological architectures, a totally different reality emerges. Adding redundancy doesn't always prevent failure. A lot of times, it silently creates fragility. There is an unseen structural force at play here, one that takes perfectly rational local optimizations and turns them into the literal architecture of global collapse. Section 1: The Illusion of Safety. Let's look at a really tangible physical system. Imagine a massive, critical load, a huge weight that absolutely has to be held aloft at all times. Beneath it, holding it up, is a single support beam. It's a very simple, linear relationship. The structural dynamics here are completely visible to us. If that beam starts to crack, you see it right away. If the load shifts, the strain is entirely observable. But obviously, a single point of failure like that is totally unacceptable in critical operations. So we optimize the system for statistical availability. Engineers aim for the famous 5 nines, 99.999% uptime. By adding redundant components, failure is made to seem mathematically impossible at the local level. We design the system so that a disruption to our single support beam doesn't bring down the load. Section 2: The Burden of Redundancy. So we return to our physical structure. To guarantee that 99.999% availability, we add rigid, redundant backup braces all around our central beam. The structure is now heavily reinforced. It certainly looks safer, but observe what has physically happened here. We've exponentially increased the mass, the stiffness, and the overall constraint of the entire system. And this is where a critical behavioral shift occurs. In a fault-tolerant system, those redundant paths actively mask early component degradation. Because the new backup braces are absorbing the weight, the original central beam can actually fracture, rot, and fail completely silently. The system continues to operate perfectly on the surface, while it is fundamentally degrading from the inside out. We've essentially traded local component failure for global system blindness. The exact mechanisms we designed to isolate faults are now actively interfering with our ability to detect them. Because the system is so good at successfully hiding small errors from the operator, the scale of the unseen risk is allowed to grow completely unchecked beneath the surface. Section 3: The Loss of Alternatives. Now our physical structure evolves again. We aren't just dealing with static braces anymore. The components are now automated and interconnected. The redundant braces are wired together with interlocking sensors, programmed to instantly react and redistribute weight the very microsecond any shift is detected. The system is managing itself at speeds human operators literally cannot match, cementing an irreversible lock-in. And a terrifying behavior emerges from this. A system that has become this hyper-optimized, heavily redundant, and entirely interconnected loses all of its slack, zero delay. There are no alternative paths for the energy to travel anymore. Every single component is completely dependent on the instantaneous reaction of every other component. We can finally put a name to the mechanism at work here: tight coupling. Identified by sociologist Charles Perrow, tight coupling happens when you have reciprocal interdependence across units, with zero tolerance for delay or modification. The severe loss of flexibility we just watched wasn't an accident. It wasn't operator error. It was a mathematical certainty of this heavily redundant design. Before we continue, I want to briefly mention an app I built called Sift. It's designed to be a calmer way to stay informed. It highlights only the most important news, completely avoiding endless headlines and sensational content. If that sounds interesting, you can find a link in the description. Now, let's get back to our explainer and look at what happens when a tightly coupled system encounters an anomaly. Section 4: The Architecture of Collapse. There is a very dark, real-world irony to this exact structure. When we look at historical events like the Chernobyl disaster or the 3 Mile Island accident, we find a chilling pattern. In many of these cases, it was the staggering complexity of the redundant safety systems themselves, or the very act of testing those backup systems, that initiated the catastrophic meltdown. The safety mechanism became the fatal flaw. This brings us to what Charles Perrow famously defined as the normal accident. In a tightly coupled, highly complex system, unpredictable cascades of interacting failures aren't anomalies at all. They are normal. They are an inevitable, unpreventable reality built directly into the fabric of the technology itself. Global failure is a feature of the design, not a bug. Section 5. The boundary of resilience. The core problem really lies in how we engineer defense in the first place. We build systems for robustness, highly rigid, specialized defenses designed to block specific, anticipated hazards. But that is entirely different from true resilience, which is the actual capability needed to survive and adapt to completely unanticipated, unknown shocks. Safety researcher David Woods introduced a brilliant concept called graceful extensibility. It's the ability of a system to stretch, to develop brand new capabilities, and to adapt precisely at the moment its existing planned capacity is completely exhausted. To survive a surprise, a system absolutely needs soft boundaries that can stretch. To really grasp this, safety researcher Richard Cook points to the biological archetype of bone. Bone is incredibly resilient because it relies on continuous strain, minor destruction, and dynamic regeneration to constantly adapt its shape to new stresses. By contrast, our engineered, heavily redundant braces are dead. They lock into permanent rigidity. They cannot grow a new path when they get surprised. So what happens when an engineered, tightly coupled system hits a hard boundary and runs out of its pre-programmed redundant paths? It experiences what Woods calls decompensation. It is the total, instantaneous exhaustion of capacity. There is no graceful stretching here. The system simply falls right off a cliff. Section 6. Following the structure. We look one last time at our physical system. It has reached maximum redundancy. Suddenly, the load shifts, a completely unmodeled, unexpected disturbance. The automated sensors trigger instantly. The redundant braces attempt to transfer the immense force, but because there is zero slack, zero time buffer, and absolutely zero ability to gracefully extend, the force has nowhere to go. The entire rigid structure shatters simultaneously. When we look at the rubble of these complex, highly optimized, hyper-redundant architectures, we can't just blame operator error or a bad component. The collapse was the only mathematically possible outcome of its rational, tightly coupled design. The system was never failing, it was following its structure.